called volumes of revolution. So instead of just doing the area of a curve, now we're going to be looking at a volume of something. Okay, so where should we begin off? Um, well, the idea of what is a volume of revolution. Hang on, let's take a look at this one. Remember how you had the area under a curve? If you take that area and you spin it in a circular method around the x-axis, you're going to get something like this. It's called a volume of revolution. If you Google images of volume of revolution, you'll see lots of these things. It's kind of like a vase or something like that, right? If you think about, okay, so the area underneath like a square root, if you were to spin that around, you're going to get something. It's actually called a paraboloid when it's actually round like this, but this one is solid, right? Now they don't have to be solid. We can also do area in between two curves and you'll end up with something that's hollow. That's later on. That's called the washer method, but for now we're just going to do discs. Now a bunch of discs is kind of like, I like to liken it to like a bunch of barbells. If you had a whole bunch of weightlifting things and you have all these round plates, they call these plates, or they also call them discs, right? The area underneath a curve, we did that with a rectangle before. Well, if you did a whole bunch of them together, like an integral, you're going to get a bunch of discs. So think of it like the ends of a barbell or something like that. So that's really going to be the shape that we're dealing with. Okay, so let's get to our notes here. Okay, boom. And where's my notes? Come back. There they are. So here's where we're going to start. We're going to start with the area of a circle. Now remember, the area of a circle is pi r squared, right? Pi times radius squared. So here's what we're going to do. We're going to start with some function. I'm going to call it f of x, and let's just say it's a straight line, something like this. So this is y equals some function of x, right? Now let's just update this. Boop, boop, boop. Go to there. Y is equal to some function of x. Okay, so if I think about the area, or not the area, but the height underneath here, right? So let's think about the height. If this is the x value, this is really what f of x is, right? This means the height at that one point. Boop. So if I think about the height, if I'm going to take that and if I spin it around the x-axis in this direction, I'm going to get something that looks completely different. Okay, so let's do this. There's my function. Y is equal to some function of x, right? That's going to get in a round kind of fashion. This is going to be round there. So you're going to get a mirrored image. So this is going to go below. Here, I'll show you. That's the axis of rotation. So this is going to be a solid, and this is called a solid of rotation. And remember, the height is underneath here. This is the f of x. The height at any point, this is really what f of x is, right? It's the height, and it's really the radius. If you were to look at it dead on, it's going to look like a circle, and that is the radius. Yeah, so looking at it dead on, I would get something like this. Looking like that. So that height there is the radius. So that's really what we're going to do. So the radius is the function f of x, right? So instead of pi r squared, here's what we're going to end up with. Pi radius squared is going to become pi function squared. Okay, so see if I can do this as a bunch of plates. Okay, I don't know if I can do this diagram, but think of it. There's one, and it has a specific thickness. And then the next one's going to be a little bit better. Specific thickness. Then the next one's going to be even bigger. Oh, this is a terrible diagram. And then the next one's going to be even bigger. So these are a bunch of discs or plates, if you will, and they're just getting a little bit bigger. The radius is getting bigger and bigger each time. See if I can shade this in a little bit. There's one. So you can see that this is the the outer edge, if you will. So if you think about it, and now here's the thing, this is all being spun around the x-axis. So far it's going around the x-axis, right? Yes, we'll change that later, but for now we're just going to start it as going around the x-axis. So this function, if you think about way back when we did this as a bunch of rectangles, you remember that? One of those rectangles becomes one of these plates or one of these discs. So if you add them all up, pi r squared really just becomes, well, pi function squared, f of x squared, right? And when you add up a whole bunch of them, an infinite number of them, that's where we got the integration. And we were integrating from left to right, that's dx. If this is a function of x, I want this to be dx. So really, this is going to be what we're using. Instead of just the integral of a function, it's the integral of a function squared, and it's times pi. Why is it times pi? Well, because pi was originally here as pi r squared, because we're doing it in a circular method. So this is really going to be it. Here's our volume. It's pi, the integral from a to b, f of x squared dx, if I'm going around the x-axis, right? If I'm spinning around the x-axis. In other words, if everything's a function of x. Now, you could also do it around the y-axis. Okay, well, let's just do it. Now, it's not going to be the same a and b. It would be from f of a to f of b. Well, let's just call it from c to d, from top to bottom or bottom to top, right? This would be f of y squared dy if it's around the y-axis. So yeah, later on we will change some of these to be functions of y, but for now, let's just start off with a function of x. Okay, so let's do that. Let's give this a shot. So sketch and find the volume of this solid, and it's going to be rotated around the x-axis. X-axis is good because that means it's going to be dx. I know that. It'll just make my life easier. dx. Everything's going to be a function of x. Okay, so this is a parabola. It's an upside down parabola. It's up 9. And I know that 1, 1, 2, if I was to go, it'll come down and hit at 3. So this is some parabola that looks something like that, okay? And I'm going to be spinning it around the x-axis in this rotation. This is the axis of rotation. Now, I know that there's an infinite area, but let's just consider this area here in the first quadrant, okay? So we're going to go from 0 to 3. So if I spin that around the x-axis, well, what's this thing going to look like? If you think about it, it's going to be a mirrored image there. However, the whole thing is circular in this, so this is where it gets a little bit ugly. Okay, these are kind of hard to draw. It might be easier to draw it over here. Something really tall. Oh yeah, I lost it there. Let's try this again. So it's going to look oval in shape, right? But the outside curvature is going to go to there. Boop. And I always like to put the center there so you can see that's the axis around which it's spinning. Okay. So it's going to be a solid that looks something like this. It's weird to kind of draw. However, the nice thing is they're not hard to do the math for because here's the volume. The volume is pi, the integral, I'm going from left to right, so from 0 to 3, right? We're just doing this finite area. I know the area goes on forever, but quite often we just use the area in the first quadrant, or it'll usually be defined as an interval. Okay, so it's going to be pi function squared, and the function is really, if you think about it, the function is the height from here to here, right? That's just, there it is. Y is equal to 9 minus x squared. So it's going to be the function 9 minus x squared squared dx. Done. That's it. Now it's just a matter of let's figure this out. Now, yeah, pi, I know that this is from 0 to 3. This is really going to be 81 minus 18x squared plus x to the power of 4 dx. If you really wanted to, yep, we could do this as the antiderivative. So this is going to be 81x minus 6x cubed. 6x cubed, right? Increase the power, divide by 3, plus 1/5 x to the power of 5, and I'm plugging in 3 and 0. I'm going to get some ugly You know what? We're doing this on the calculator. Plug this into your calculator because quite often some of these are going to get really, really ugly. This is going to be pi times 129.6, right? Now that's not really exact because pi is exact. Now you might see this, but you know what? That's fine. It's just a number. We're going to be plugging these into our calculator. We're not doing these things by hand because, I mean, that's just some ugly algebra if you really will. You're plugging in 3 into all these things. Okay. Let's try another one. Sketch and find this volume. Okay, so now this is x squared divided by 3. Okay, so I know it's going to be a half parabola. Well, it's kind of a parabola divided by 3. It's rotated around the y-axis. We need to figure out some interval. I don't want this to go on forever. What do we want to use? Let's say on the interval from, I'll just make this up, from 0 to 3. Right? 1, 2, 3. So when the x value is 3, the y value is going to be 9 over, oh, nice. There's a reason why I chose that one. Okay. So this is not going to be 1, 1. This is going to be like a third. So this is going to be a parabola that has curvature like that. Okay. So f of x, now we're not spinning it around the x-axis. Now we're spinning it around the y-axis. I want everything to be dy. I want this to be a function of y. Right now it's written as a function of x. Okay, so in other words, this is going to get spun in that direction. That's going to go over to here. Oh yeah, this is going to change this thing. It's going to get, I'm going to get a mirrored image over there, and it's going to be, okay, yeah, that's a mess. It's going to look like a bowl. It's going to look something like that, and then there's the curve, right? There's the outside curve. That's what this is. This is a solid of revolution. It's going to look something like, okay, yeah, this is, I've lost it there. But you can kind of see this is the rotation in this direction. So I'm not going to be dealing with the function. I don't want this part. I want this part. So if this was f of x, right? This part here is actually f of y. That's what I'm interested in. Okay, so that's the radius, right? Because that's going to be from here to here. This is f of y. F of y isn't the height under the function. Well, f of x is the height under the function. F of y is the height horizontally from the y-axis out to the function. That's the height under, if you want to think about it in terms of y, right? This would be f of y as we're going. Yeah, as we're going along the curve, f of y is getting bigger, right? It's longer. Now, I'm not going over here. No, let's not do that. We'll just do it in the first quadrant. So this, I'm going to be spinning it in this direction. Okay, so step 1. Everything here needs to be a function of y, not x. So right now I've got y is equal to x squared over 3. We need to solve for x. So in other words, 3y is equal to x squared. X is equal to the square root of 3y. Hang on, this means f of y is the square root of 3y. Shouldn't it be plus or minus? Yeah, you see it? There's the plus, there's the minus. You know, we're not using the minus part. So that's why in this case, I could actually kind of forget about the plus or minus. I'm only going to use 1/2. I'm only going to use the right-hand side over here. You don't need to use both because as soon as you go in a full circle, right, 360 degrees, this is going to go through all. Now, if you use both of them, you're going to double up your answer. You don't want that. Okay, so there's my function. Okay, and so what is my volume? The volume is going to be pi integral dy. There's my function, 3y, and that's being squared. Okay, this is nice because it simplifies really good. And from 0, hang on, what's the, oh, I don't know the intervals. Yes, I do. Now the x interval is from 0 to 3. So the y interval is from 0, luckily it's the exact same 0 to 3, which that's why I chose 3 because I knew that it was a nice number. But it's going from the y, so I'm integrating along the y, from 0 up to 3. So this is going to be from 0 to 3. Now this is a pretty easy one to figure out, right? 0 to 3, 3y dy. We can actually do this one without a calculator. This is pi, this is 3 over 2, y squared, and I'm plugging in 3 and 0. The nice thing about plugging in zeros, they just disappear, right? So this becomes pi times, what do I have? 3 over 2 times 9 minus 3 over 2 times 0, right? I don't need to show that. I know that this is. So I'm going to get 27 over 2. In other words, I'm going to get 13.5. 20, they'll probably write it as 27 over 2 pi as exact in the back of the book. But I mean, yeah, we know that that's 13.5. Now, there would be some say, oh, this is improper because that, but it's still exact, right? Did the exact same answer. You know what? If you want, turn it into a decimal. Quite often we'll usually just go to 3 decimals for these. Okay, so the math for here is not actually that bad. Really, the tough part is figuring out what does it look like. So for each one of these questions, typically I make them about 3 marks, right? This is 1 mark. I just want a little sketch. Do you know it's going this direction or is it going this direction? Because there's a big difference. There's the second mark. You set it up, right? You have to figure out the interval. You know it's pi and it's the function squared. Is it dx or dy? And then there's the third mark. Typically, there's worth 3 marks. 1 for a diagram, 1 for setting it up, and you know what? You don't need to show this work because I know you can do it on a calculator. Alrighty, good luck with these.